In this video, we'll be learning to name chemical compounds. The first chemical compound we want to try to name is binary ionic compounds of type 1. Now, the word binary in this case refers to the fact that these compounds have two elements that make them up. Ionic tells you that one of the elements is a metal, one is a nonmetal. And type 1, refers to the metal specifically. A type 1 metal is a metal in which we know the charge on the metal from that metal's location in the periodic table. There are some elements that we know that in ionic compounds what charge they actually possess. For instance, all the alkali metals here in the first column, they all possess a +1 charge when they are in ionic compounds. Column 2 here, they all possess +2 charges in ionic compounds. At the other end, we have some nonmetals that do the same thing. The halogens all in ionic compounds have a -1 charge. Oxygen, sulfur, and selenium have a -2 charge. Nitrogen and phosphorus and arsenic have a -3. Carbon, -4. And so the other ones we have are aluminum, which has a +3 charge in ionic compounds. Zinc, which has a +2 charge in ionic compounds. And silver, which has a +1 charge in ionic compounds. So these are the type 1 metals. To name these compounds, it's a very simple matter of first naming the metal. So in this case, Ca is calcium. So first we name the calcium. And then you name the nonmetal, the anion, with an IDE ending. So this was oxygen, or is oxygen. And so I change the ending to an IDE ending, so this becomes calcium oxide. Here we see NaBr. Na is sodium. So the first part of the name is sodium. Br is bromine, so it becomes sodium bromide. Rb2O, Rb is rubidium. So the first part of the name is rubidium. The second part is oxygen, so it becomes oxide. So this is rubidium oxide. Here we have Ali3. Al is aluminum. So we have aluminum. I is iodine, so it becomes iodide. So we have aluminum iodide. So that is how we go from formulas to names for binary ionic compounds of type 1. For binary ionic compounds type 1 going from name to formula, it's a little more challenging because you've got to figure out how many of each ion you need to balance the charges. So for instance, strontium fluoride. Alright, strontium is here, Sr. We know its charge is +2 because of the column it's in. So we have Sr with a 2+. Fluoride is fluorine, right here. We know because of its column it has a -1 charge in ionic compounds, so F-. So now I basically what we call cross the charges. I look at the number here, which is a 2, and the assumed number here, which is a 1, and I cross them to the other element to make subscripts. And that then tells me that what I have is one strontium for 2 fluorines, SrF2. Aluminum selenide, aluminum, Al, right here. It has a 3+ charge. Selenide is selenium, right here. It has a -2 charge. Once again, we cross the charges. So this 3, that 2, we take them down here as subscripts. And so what do we get? We get Al2 Se3. Potassium nitride. Potassium's K with a +1 charge. Nitride is nitrogen, so N. Nitrogen has a -3 charge. Crossing the charges now, what I find is that I have K3N. Magnesium phosphide. Magnesium, Mg. According to this, in ionic compounds, it has a 2+ charge, so Mg 2+. Phosphide is phosphorus. In ionic compounds, it has a -3 charge. And so crossing the charges, I end up with Mg3P2. So that's how you go from name to formula in binary ionic compounds of type 1. If you have a metal that's not one of the type 1 metals, so basically most of the periodic table's metals, these you don't know the charge of the ion of the metal from the periodic table, so we've got to put that charge into the name. And we do that with the Roman numeral. Now how do we figure it out? We figure it out from the formula. So here I have 2 mercuries, 1 oxygen. This is an ionic compound. I know the charge on that 1 oxygen is -2. If I have 2 mercuries, and this oxygen is -2, which means all this mercury has to come up with +2 to counter that. I've got 2 mercuries, each one needs to be +1, therefore. And so how do I name this? I first name the metal just like before. So this would be mercury. After the mercury, in parentheses, I put a Roman numeral which indicates the charge on the mercury, in this case 1. So this is mercury 1 oxide. So it's not that different from naming from type 1. Down here we have FeBr3. That's iron. This is bromine. Bromine has a -1, each ion of bromine. I've got 3 of them, so I have a total of 3 negative charges here, which means this iron must have 3 positive charges. This thing, in other words, since I only have 1 of them, must be 3+. And so what do I have? I have iron 3 bromide. Here I have cobalt and sulfur. Sulfur from the periodic table, a -2 charge. I have 1 sulfur, so I have a total of 2 negative charges. I have 1 cobalt. It's got to counter that, so it's got to have a +2 charge. And therefore I name this cobalt 2 sulfide. Here I have titanium and chlorine. Chlorine from the periodic table has a -1 charge. I've got 4 of them for a total over here of -4, or 4 minus charges. This 1 titanium has to counter that, so it has to have a charge of 4 pluses. And therefore, I name this titanium 4 chloride. Alright. Now going from name to formula in this case is exactly the same as it was in the last case, in the last type, but now we have a Roman numeral that tells us the charge on the metal. So I have tin 2 nitride, tin Sn, and the 2 tells me it's 2+. Nitride, nitrogen, and from the periodic table, 3- in ionic compounds. Crossing the charges like we did last time, I have Sn3N2. Cobalt 3 iodide cobalt, CO. 3 is 3+. Iodide. Iodide is iodine with a -1 charge. Crossing the charges and balancing them, COI3. Mercury 2 oxide, mercury, Hg. This one has a 2+ charge. Oxide, oxygen. This, according to the periodic table, has a -2 charge in ionic compounds. Crossing the charges is dangerous in this case because in order to balance the charges, which is what I'm really doing, is just balancing the charges, making sure I have enough positive for enough negative, I just need 1 of each. So HgO. If you cross the charges, you get 2 of each, but then you would reduce the 2 and 2 to 1 and 1, since this is an ionic compound. Chromium 4 sulfide, chromium, Cr. This has a 4+ charge. Sulfide is sulfur. According to the periodic table, sulfur has a -2 charge in ionic compounds, so -2. Crossing the charges is dangerous again, you see, because if I do, what I end up with is Cr2S4. I've got to reduce those subscripts to the simplest whole number ratio because this is, again, an ionic compound. And so what do I get? CrS2. You always reduce the subscripts to a whole number ratio when you're talking about ionic compounds. Now, there are other kinds of ionic compounds we need to talk about, and these are ones that are not binary. These are ones where you have what we call a polyatomic ion, and here you see some of the important polyatomic ions. All right, so these are just a few of them. There's a significantly large number, but these are the big ones, the ones you see over and over again. Now, naming and formulas from names with the polyatomic ions is very straightforward because each polyatomic ion has a name, and that name just goes into the name of the formula. So BaSO3. Ba is barium. All right, barium is right here. I know it's charged from the periodic table, so I don't have to put it in there. This is a type 1 metal, in other words. So I have barium. SO3. SO3 is here, sulfite. So the name sulfite goes in the formula. And you end up with barium sulfite. Now, one thing you should notice, for the most part, the polyatomic ions all have endings that end in an ATE or an ITE, which makes them very different from the binaries, which always end in IDE. So you end up, in binaries with oxide and sulfide, but in polyatomic ions, you end up with sulfates and phosphates and sulfites. NaNO3. Na is sodium. It's right here. I know it's charged. I just need to name the metal. This is a type 1 metal again. So sodium. NO2. NO2 is nitrite. So I just put in nitrite. So I have sodium nitrite. CuMnO4 2. Cu is copper. Copper is right here. I don't know its charge. This is a type 2 metal. So I got to put copper as the beginning part of the name, but now I need to figure out its charge to put after it. I can tell its charge from the polyatomic ion, MnO4. MnO4 is permanganate. Each MnO4 has a -1 charge. I have two of them, so I have two negative charges, which means this copper must have two positive charges to offset it, because I only have one copper, you see. So this is copper 2, and then I name the polyatomic ion permanganate. Again, this is iron. This is dichromate, the dichromate ion, which has a -2 charge. If there are two negative charges here, I have two irons, which means each one must have a +1 charge. Therefore, this I will call iron 1 dichromate. Moving along, going from now name to formula, I do exactly what I've been doing. Chromium 3. That's Cr with a 3 plus. Hydroxide. Hydroxide, if I look, hydroxide, OH minus. OH minus. Note this has an IDE ending. This is one of the very few polyatomic ions that actually has an IDE ending. There's two major ones, hydroxide and cyanide. Now crossing the charges. Cr, OH, 3. I need 3 OHs because I need 3 negative charges to cancel the 3 positive charges. Magnesium cyanide. Magnesium is a +2 charged ion when it's in ionic compounds. So Mg with a 2 plus. Cyanide. Cyanide is Cn minus. So Cn minus 1. Crossing the charges again, I get Mg Cn 2. Lead 4 carbonate. Lead 4 is Pb with a 4 plus charge. Carbonate. Looking through here, I find carbonate, CO3 with a 2 minus charge. Crossing the charges and reducing, what I find is I need 1 lead for every 2 carbonate ions. So PbCO3, 2. Ammonium acetate. Ammonium is our only plus charged polyatomic ion. We see it here, NH4 plus. So we have ammonium, NH4 plus, and acetate. Acetate we see over here, CH3CO2 minus. Putting them together, crossing the charges, NH4, CH3CO2. Oh, by the way, sometimes you'll see the acetate ion written instead as C2H3O2 minus. That's just an alternate way of writing the acetate ion. This way is more chemically specific, that way is more shorthanded. But you'll often see both. Binary molecular compounds. So now we've turned our attention back again to two elements in a compound, but now we're molecular. So now these are nonmetals with nonmetals, which means you don't have ions. You just have nonmetals uncharged as neutral, which means in the name of the compound you need to specify how many of each element you have in that compound. But the naming itself, the names are the same as we've done over and over again now. So this first element is nitrogen. I have 2 of them. So I prefix it with the Greek word or Greek prefix for 2, which is di. So this becomes dinitrogen. I have 4 oxygens. 4 is tetra. So tetroxide. Dinitrogen tetroxide. Here I have ICl3, iodine. Now, you would think to put mono on this because there's only one of them, but the rule is if you have only one of the first element, you leave the mono off, but only of the first element. So I have one of the first element, I leave the mono off, so this is iodine. Because there's 3 chlorines. SO2 minus. S, I have one of them. Sulfur. Dioxide, because I have 2 oxygens. 2 phosphoruses, so diphosphorus. 5 is penta, so pentasulfide. And there we have going from formula to name for binary molecular compounds. Now, turning our attention once again to a different, or going the other direction, I should say, from name to formula. All right? And these are actually quite easy. You just identify the element symbol, and you figure out how many you have. So, diboron trioxide. Boron, B. How many do I have? I have 2 because of the di. Oxide is oxygen, O. How many do I have? 3 because of the tri. So B2O3. Arsenic. There's no prefix, it's the first element, therefore there's one of them. This happens to be As, in case you are curious. Pentafluoride. Fluoride is fluorine, which is F. Penta means 5, so this is AsF5. Dinitrogen, N2. Monoxide. Oxide, oxygen, Mon 1, so O. N2O. Sulfur, no prefix, S. Hexachloride. Hexa is 6, chloride is Cl, so SCl6. So going from name to formula of a binary molecular compound is quite simple, actually. You just pull the numbers of each element from the name itself. And finally, the last class of compounds we need to learn to name right now is acids. All right, acids, all acids have a cation, the same cation. They all contain H+. That sort of goes with being an acid. So really we spend most of our time on these problems naming the anion and figuring out how to name it. So basically in this case naming the C2H3O2 or the IO4 or the NO2 or the I. So as I told you in a previous slide, C2H3O2 is another form of what we normally see as acetate. Alright, now here are the rules. If you have a polyatomic ion that ends in ATE, you change the ATE ending to an IC ending. So this was acetate, now it becomes acetic. And then you tack on the word acid to indicate that it starts off with H+. So you have H+, that says it's because of the acid. acetic cis acetate, which tells you the anion. You can put it together. We'll show you that on the next when we go from names to formulas. HiO4. Again, it's an acid because the H comes first. IO4. IO4 is not on here. However, what we see is a family of a different halogen. ClO4 minus, ClO3 minus, ClO2 minus, ClO minus. Well, it turns out that that trend exists for all the halogens. All the halogens have those four. In other words, there's an IO4 minus, an IO3 minus, an IO2 minus, and an IO minus, and the naming's very similar. The first one here is perchlorate, so for the IO4 minus, it'd be periodate. Iodate, iodite, and hypoiodite for the I versions of all those. So here I have IO4 minus, which will be periodite. So periodite becomes periodic, or more properly pronounced, periodic. But it's really just periodic acid because it comes from periodate, which comes from perchlorate, which is just what we see there in the table. Next acid you see, HNO2. NO2 we see here is nitrite. Nitrite. Now, if we have a polyatomic ion that ends in ITE, that ITE becomes a new ending, OUS. So nitrite becomes nitrous, and I tack on the word acid to indicate the H+. So this is nitrous acid. And now I have a new case. This is binary now. This is a binary acid. And binary acids always, their names always start with one thing. And it tells you that this is binary. It starts with hydro. That tells you this is a binary acid. And from there you name it the way we've been naming it. This is iodine. Iodine, the ending for all binary acids are IC. So iodine becomes iodic. So this is hydroiodic acid. So this is why when we have HCl, alright, Cl's chlorine, this is binary. This is why this is named hydrochloric acid. Alright, hydro tells you binary, chloric gives you the anion, the acid tells you the H+. So let's now turn our attention and look at the going from name to formula now. Hydrobromic acid. This is binary, and I know that because of the hydro. Bromic must mean bromine. Acid means H+, so I have an H+. I have bromine ion. This is binary, remember. Bromine minus 1 charge. Crossing charges HBr. Chlorous acid. Oh, okay, so no hydro. This is polyatomic chlorus. OUS came from ITE. This is chlorite. Chlorite is ClO2 minus. So I have the H+ because of the acid. I have the ClO2 minus because of the chlorite. And so this is HClO2. Nitric acid. No hydro, which means that this is not binary. It's polyatomic. Alright, I know I have the H+ because of the word acid. Nitric came from nitrate. Nitrate is NO3 minus. NO3 minus, putting this together, HNO3. Sulfuric acid. Again, no hydro. This is polyatomic. Sulfuric came from sulfate. Sulfate is right here, SO4 2 minus. So I have the H+ from the acid, the SO4 2 minus from the sulfate, putting this together, H2SO4. And so sulfuric acid's formula is H2SO4. And so this is how we name the major classes of compounds we're going to be dealing with in general chemistry. All right, there's a vast amount of naming that goes on in other parts of chemistry that we're not going to cover in this class, but this is the ones that we cover and then we're going to deal with a lot. We need to understand these early on. We need to get mastery of these early on because they're going to come back to haunt us if we don't. Because a lot of times when we talk about chemical reactions in later chapters, we're going to talk about them in terms of the names of the formulas, what's the reactant name, what's the other reactant's name, what the product's names, and we need to be able to go quickly from name to formula or formula to name, so we need to gain mastery of this now.